Hello guys, so in this lecture I'll be extending the discussion on nonlinear regression functions, and I'll be discussing the interactions between independent variables. So the outline of this lecture is that the first part will contain nonlinear functions of two variables, meaning we'll mostly be dealing with interaction terms between two independent variables. And then the last part will basically look at the application of this kind of strategy of using interaction terms to the California test score dataset, which we have been working with when we are looking at the relationship between student-teacher ratio and test scores. So what does it mean when we talk about interactions between independent variables? So what we are basically looking at is that perhaps a class size reduction is more effective in some circumstances than in others. For example, if we take English, the percentage of English learners in the classroom, maybe smaller class sizes help more if there are many English learners, and maybe the opposite is true, that it helps students more when there are less English learners in the classroom to reduce the student-teacher ratio. So what we are essentially looking at is that the change in test score over change in student-teacher ratio, this slope, essentially slope, might depend on the percentage of English learners in the classroom. So if that is the case, if the economic theory driving this relationship is such that you believe that the percentage of English learners in the classroom might actually be affecting the relationship between student-teacher ratio and test scores, then interactions provide a way forward, and they basically give you a more accurate idea about how the relationship between student-teacher ratio and test score will be. So how do we model such interactions between any x1 and x2? So there are different possibilities as far as interactions are concerned. So x1 and x2 can be binary variables, or they can be continuous variables, or one of them can be binary and the other one can be continuous. So we'll cover all three of these cases, and we will see how interactions differ for all three of these cases, but also are similar for the most part. So first of all, we will take a look at the example of interactions between two binary variables. So this is the equation in which, regression equation in which you have two binary variables, d1 and d2. Both of these can take only two possible values, 0 and 1. So beta 1 is the effect of changing d1 from 0 to 1, and beta 2 is the effect of changing d2 from 0 to 1. So in this scenario, in this regression equation, the effect of changing d1 does not depend on the value of d2. So how do we introduce an interaction term? That's what we are doing in this equation over here. So what we do is that we include another variable, which is the product of d1 and d2. So this can be called, or is called, your interaction term between d1 and d2. So obviously when you include another variable, which is the multiple of d1 and d2, you will also obtain another coefficient when you are estimating this regression equation. So let's see how this interaction effect, or this addition of the interaction effect, changes our results for the effect of d1 and d2. So if we estimate this regression equation with the interaction term, what you can do is that if you are trying to find the effect of changing d1 from 0 to 1, you can compare the two cases. So first, the case is that you will basically take d1 equals to 0 for a given value of d2. And then you will compare this case against the case of when d1 is equal to 1 for the same given value of d2, which is denoted by this small d2. and in that way you will see how much of a change in the value of y is occurring. So if we plug in a value of d1 equals to 0 into this equation, what we get is that this coefficient goes away, this coefficient remains, beta naught coefficient remains, and this coefficient also goes away, because when d1 is equal to 0, this whole interaction term becomes 0. So what we end up with is beta naught plus beta 2 d2. d2 is small d2 is the value of the larger, or the capital D2 that we have to use when we are comparing the two cases. So the second case is that the value of d2 remains the same, which is small d2, but the value of d1 changes from 0 to 1. So when we substitute 1 instead of d1 in this regression equation, let's see what we end up with. We end up with beta naught plus beta 1 plus beta 2 d2, and this interaction term will also be included, because when d1 is equal to 1 and d2 is equal to small d2, then you get beta 3 d2 over here. So this is the total conditional mean. This is the conditional mean of y when d1 is equal to 1, and this is the conditional expectation of y when d1 is equal to 0. So this first equation is our equation B, and the second equation is our equation A. So if we subtract A minus B, we actually get the effect of changing d1 from 0 to 1 for a specific value of d2. Let's do that. So when we do this, we get beta 1 plus beta 3 d2. And it's easily seen from the comparison of these two equations that beta naught will be cancelled out when we are subtracting, and also beta 2 d2 will be cancelled out when we are subtracting. So we will just end up with beta 1 plus beta 3 d2. So now we can see that because of this existence of d2 over here, it shows that the effect of d1 on y depends on d2, and that is what we wanted to incorporate in our regression. When we tried to introduce the interaction term, we wanted to see how different values of d2 will affect the relationship between d1 and y. So now we have achieved that, because we are looking at this term d2 for the effect of d1 on y expression, and that is what we wanted. And beta 3 is the increment to the effect of d1 when d2 is equal to 1. So when d2 takes the value of 1, so then beta 3 will be the increment to the effect of d1. So now let's extend this example to the relationship between student-teacher ratio and test scores. So right now we'll be creating a variable high student-teacher ratio, and that variable will take the value of 1 if the student-teacher ratio is greater than 20, and it will take the value of 0 if student-teacher ratio is less than 20. Similarly, we have another binary variable which is by the name of high English learners. Takes the value of 1 if the percentage of English learners is greater than 10 in the classroom, and it takes the value of 0 if the percentage of English learners is less than 10. So in order to incorporate the interaction effect, we basically estimated this equation for the test scores with the high EL, with high STR, and with also the interaction term between these two binary variables. And these are the coefficients that we obtained, and in the parentheses over here are given the standard errors for these coefficients. So given this information of coefficients provided in this equation, if I said that I want to know what is the mean of test scores for the group which has low student-teacher ratio and low percentage of English learners. So for that case, I will basically have to substitute 0 for high str variable and 0 in place of high el variable in this equation. When I do that, all of these coefficients go away and the mean will simply be 664.1 when the test scores are concerned for the group with low student-teacher ratio and low percentage of English learners. So what will be the mean for the group which has low student-teacher ratio but high percentage of English learners? So in this scenario, you will have to substitute 0 in place of high str while substituting 1 in place of high el. When you do that, you will get 664.1 minus 18.2 and minus 3. Well, actually, this whole interaction term will become 0 because high str will take the value of 0. So your total mean will only become 664.1 minus 18.2. So similarly, you can work out the 4 possible cases for different groups when they take different values of high str and high el, and you can figure out what the means for each of those groups will be. But keep in mind that just finding out the means is not really finding the effect. So when we are trying to find the effect of high str when high el is 0 and when high el is 1, we have to compare 2 different equations with each other. So let's take the example of finding the effect of high str when high el is 0. So in this scenario, you will basically compare 2 equations with each other. For the first equation, you will use the value of high el as 0 and use the value of high str as 1, while in the other equation you will use the value of high el still as 0, but for the value of high str you will use 0. So when you subtract both of these equations from each other, you will basically get the effect of changing high str from 0 to 1 when high el takes the value 0, and you will get the effect as minus 1.9. Similarly, if you want to find out the effect of high str on test scores when high el is equal to 1, you will once again have to basically compare 2 equations with each other. For the first equation, you will use the value of high el equals to 1 and the value of high str also equals to 1. For the second equation, you will use the value of high el equals to 1, but the value of high str equals to 0. And when you do that, when you subtract both of these equations from each other, you will get the total effect equal to minus 5.4. So let's see what these two actually mean, what these two effects actually mean. So it simply means that when high el is equal to 0, meaning when the classroom has a lower percentage of English learners, the effect of increasing the student-teacher ratio is different from when there are higher percentage of English learners in the classroom. So the effect is larger in the case when there are higher percentage of English learners in the classroom. It's minus 5.4 compared to minus 1.9 when there are lower percentage of English learners in the classroom. So it simply means that the class size reduction is estimated to have a bigger effect when the percentage of English learners in the classroom is large. So another thing that you should always be looking at is whether this interaction term or the coefficient of the interaction term is significant or not. So when we actually find this significance, it shows that 3.5 divided by 3.1, which is the standard error, will not lead to a t-stat, which will show significance for this coefficient. So this coefficient, this interaction coefficient, is not really significant, so we should not really put too much value in this term. So this slide further explains what I meant when I was talking about the means for the 4 different groups which are possible between these between the interaction of these two variables, high STR and high EL. So these are the means for the different for the 4 different groups. So for example, the mean for low EL and low STR is 664.1. On the other hand, the mean for high EL and high STR is 640.5, and these can be obtained when you plug in the values of STR and EL into this equation over here. For example, let's try to figure out the mean for high EL and low STR. So in this scenario, you will plug in 1 instead of high EL and 0 instead of STR. So let's see what the mean will come out to be. So it will be 664.1 minus 18.2, and both of these terms will become 0 because high STR will be equal to 0. So 664.1 minus 18.2 is actually equal to 645.9. You can similarly find out the means for all 4 of these groups by plugging in the relevant values for STR, high STR and high EL into this equation. Just as an exercise, you should try to do that so you are clear on this concept. So now we will take a look at the example of interactions between continuous and binary variables. So this is an example of a regression equation in which D is a dummy variable or a binary variable and X is a continuous variable. But in this regression equation, there is no interaction term, meaning the effect of X on Y does not really depend on D. In order to find that how much will be the effect of X and Y when it also depends on D, we have to introduce this interaction term into this equation, which is once again just the multiplication of the 2 variables D and X. Obviously, when you include this variable, it will also yield a separate coefficient, and we will see how this coefficient actually will affect the relationship between X and Y. So with this sort of an interaction term where one of the variables is a continuous variable and the other variable is a binary variable, you will basically end up with 2 separate equations for the 2 categories of D. So let's see what I mean by this. So for example, when you are trying to find the equation for when D is equal to 0, just substitute the value of 0 in place of D in this regression equation, and what you end up with is beta naught plus beta 2xi, because both of these terms will become 0 because D takes the value of 0. Similarly, if we plug in the value of D equals to 1, we will find the equation when D is equal to 1. And when that happens, this is the equation that you will get. Alright, so what does this mean then? It means that the intercept of this equation will become beta naught plus beta 1, while the slope of x will become beta 2 plus beta 3. So you can clearly see that these 2 equations are totally different as far as their intercepts are concerned, and also as far as their slopes of x are concerned. So what this simply means is that when D is equal to 0, the line of best fit will be having a different intercept as well as a different slope than when D is equal to 1, and the line for that will also have a different slope and a different intercept. So what we just covered would be shown by this example B over here, where you have different intercepts and different slopes for when D is equal to 0 and when D is equal to 1. So the question then arises, what is this first case where the intercepts are different but the slopes are the same? So that will be for the scenario when you don't include an interaction term in the regression equation. So you will essentially have two different equations for when d takes the value 0 or 1, but in both of these equations only the intercept will be changed and the slope of x on y will not really change. Now the final question arises, when will we get to this third scenario, part C, where you have the same intercept but different slopes? So this scenario can be reached when you introduce the interaction term, but you are not including d as a separate variable in the equation. So in essence, your regression equation is y equals to beta naught plus beta 2 xi plus beta 3 d multiplied by x. So you're not including d separately in the equation. If you do that, then you will get two different equations with two different slopes for when d takes the value 0 and when d takes the value 1, but both of them will have the same intercept. So let's see how we can actually interpret the coefficient in the scenario when one of the variables is a continuous variable and the other variable is a binary variable. So once again, you have to compare two different scenarios with each other. So the first scenario is that you are basically estimating the value of y for when for a specific value of d and for also a specific value of x. Now there is a slight change in the value of x denoted by this change in x over here, and now you will have to substitute that total value of x into the second equation in order to compare both the scenarios. So obviously this change in x will be also yielding a change in y. And when you substitute this change x plus change in x over here instead of x, you will have to do it in both the places where x occurs. And when you do that, you can compare scenario A and scenario B. So when you subtract A minus B, you get change in y equals to beta 2 change in x plus beta 3 d change in x. So if you take change in x common on this side and take it to this side over here, to the side of y, you will get change in y over change in x equals to beta 2 plus beta 3 d. So now we are getting what we wanted. The effect of x depends on the value of d. So if we are finding out how much is the rate of change of y compared to rate of change of x, or rate of change of y over rate of change of x, that value will depend on whatever value d also takes. So beta 3 essentially becomes your increment to the effect of x when d is equal to 1. So now let's extend this kind of an interaction term scenario to the example of test scores and student-teacher ratio. So over here, the student-teacher ratio is a continuous variable, while the high EL is a binary variable, which basically means that when it takes the value of 1, it shows that there is a high percentage of English learners in the classroom. When it takes the value of 0, it shows that there is a low percentage of English learners in the classroom. And obviously you will also have to include this interaction term over here. So when we estimated this equation, the following coefficients were obtained along with these standard errors. So just like what I explained in the previous slide, what you have to do is that you have to basically look at two different equations for when high EL takes the value of 0 and when high EL takes the value of 1. So you simply substitute high EL equals to 0 into this equation, and it will yield you 682.2 minus 0.97 STR. On the other hand, when you substitute high EL equals to 1 into this equation, it will yield you 687.8 minus 2.25 STR. obviously this leads from the calculation over here. So the first thing to notice is that we get two regression lines for when high EL equals to 0 and when high EL equals to 1. And in both of these lines you can see that the intercept are different from each other, and also the effect of student-teacher ratio on test score is different in both of these equations. So it simply means that the class size reduction is estimated to have a larger effect when the percent of English learners in the classroom is large. So it simply is shown by this higher coefficient compared to this lower coefficient over here. So what this means is that when you reduce the student-teacher ratio by 1, the average test scores when there is a higher percentage of English learners in the classroom goes down by more than when there is a lower percentage of English learners in the classroom. This can be because of a number of different reasons, because if the student-teacher ratio is reduced, maybe students who are still learning English can get more one-on-one attention from the teachers, and that's why it can result in a higher increase in their test scores. So a little bit more on this post-estimation of this regression equation with the interaction term. So right now what we are doing is that we are testing different hypotheses. So let's suppose we are testing the hypothesis that the two regression lines have the same slope. What do we have to do? So since the slope is different because of this coefficient of the interaction term, what we have to do is that we simply have to see whether this coefficient of minus 1.28 is a significant coefficient or not. So we simply divide minus 1.28 by the standard error to get the t-stat, and this t-stat shows that we cannot reject this hypothesis at the 5% level of significance. Now let's see another hypothesis. Now we are testing the hypothesis that the two regression lines have the same intercept. Now the intercept is different because of the slope of high EL. And you can also take a look at why that is the case when you go back to the previous slide. So you can see that the intercept is different from 682 in the first equation, because 682 plus 5.6 becomes the new intercept for when high EL is equal to 1. So essentially this coefficient 5.6, the coefficient of high EL, determines the change in the intercept between the two equations. So that's why, to test this hypothesis that the two regression lines have the same intercept, we basically just have to see whether the coefficient on high EL is 0 or not. So the t-stat that comes out to be from here, when we divide the coefficient by standard error, is 0.29, and you cannot reject the null hypothesis that the coefficient on high EL is 0 at even the 10% level of significance over here. So what it simply means is that when you are looking at the individual coefficients, minus 1.28 and 5.6, both of these are not significant at the 5% level of significance. So what you can also take a look at is that the two regressions, or you can test for the null hypothesis that the two regression lines are the same. So in this scenario, you are doing a joint hypothesis testing for that the coefficient of high EL and the coefficient of this interaction term STR multiplied by high EL are jointly equal to 0. Now this joint hypothesis is rejected at the 1% level of significance because you're using the F stat over here, and this F stat will be obtained by Stata if you actually run this test on Stata. So in this scenario, what should we do? Because the joint hypothesis test tells us that the two regression lines are not the same, while the individual t-tests are telling us that the two regression lines have the same slope and they also have the same intercept. So more importantly, why is this the case that the joint hypothesis rejects the null hypothesis while the individual hypothesis with the individual t-tests do not reject the null hypothesis? It's simply because both of these variables, the STR, student-teacher ratio, and high EL are very strongly correlated with each other. And that is because the coefficient of their interaction term does not come out to be significant. So now we will turn our attention to the last scenario in which both of our variables are continuous variables and we are introducing an interaction term between the two in the regression equation. So the scenario x1 and x2 both are continuous variables, and if we just estimate this equation over here, the effect of x1 on y in this equation does not depend on x2. So in order to capture that, we will have to introduce an interaction term into this regression equation, and when we do that, we can compare how the value of x2 will determine the relationship between x1 and y. So let's see how we can do that. So the general rule once again is that we have to compare the different cases. So in this scenario, we will start off with initial values of x1 and x2 and plug those in into this regression equation over here, and then we will also plug in the value of x1 plus the change in x1 into the second equation, and obviously this change in x1 will also yield a change in y on the left hand side. So when we plug that in to this equation and then we subtract this equation A minus equation B, we get change in y equals to beta 1 change in x1 plus beta 3 x2 multiplied by change in x1. Once again, if we take change in x1 common on this side and take it to the left hand side, it will become change in y over change in x1. So this gives us a nice expression for change in y over change in x1, and you can see that the effect of x1 on y essentially also depends on the value of x2 over here. And that is what we wanted to capture, and that is what we are getting by after introducing the interaction term between x1 and x2. So once again, beta 3 can be termed as the increment to the effect of x1 from a unit change in x2. So remember that x2 now is not a binary variable, so that's why this is not the increment to the effect when x2 is equal to 1, but instead it is the increment, beta 3 is the increment to the effect of x1 from a unit change in x2. So extending this to the example of test scores, or to the relationship between test scores and student-teacher ratio, in this regression equation, both student-teacher ratio and the percentage of English learners are continuous variables, and we are also introducing an interaction term over here between the two variables, and you can see that we already have the coefficients and their standard errors post estimation of this regression equation. Now, if you have to find out, if you are trying to find the effect of change in student-teacher ratio on test scores, that comes out to be minus 1.12 plus 0.0012 multiplied by percentage of English learners. So essentially shows that the relationship between student-teacher ratio and test scores depends now on the percentage of English learners in the classroom. So what will be the slope or the effect of student-teacher ratio on test scores when the percentage of English learners is 0 in the classroom? When we plug in this value into this expression over here, we get minus 1.12. Instead, on the other hand, if the percentage of English learners in the classroom is 20% and we plug that in here, over here in this expression, in order to find the effect of student-teacher ratio on test scores, we get an effect of minus 1.10. So this simply means that when the percentage of English learners in the classroom is lower, the effect of decreasing the student-teacher ratio on test score will be higher than when the percentage of English learners is higher in the classroom. That effect of decreasing the student-teacher ratio on test scores will be slightly lower. So once again, coming to hypothesis testing post-estimation, when we try to see that when we try to test the null hypothesis that the population coefficient on the interaction term is equal to 0, we cannot reject this null hypothesis at the 5% level, and you can simply calculate the t-stat by using this coefficient and the corresponding standard error. Similarly, if you are testing the null hypothesis that the population coefficient on STR is equal to 0, we can also not reject this null hypothesis at the 5% level of significance. So why are we first of all testing both of these coefficients? Because our main variable of interest is STR, and we are interested in the relationship between STR and test scores. So the two coefficients that involve STR are this coefficient over here and the interaction coefficient, but both of these cannot be rejected at the 5%. The null hypothesis that both of these are 0 separately cannot be rejected at the 5% level of significance. But what about their the null hypothesis that they are jointly equal to 0? So when we do that, you'll basically get this f-stat, and this f-stat can be rejected at the 5% level of significance because the p-value comes out to be 0.021. So once again, we are left with the scenario that the individual null hypothesis for the individual coefficients cannot be rejected at the 5% level of significance, but the joint hypothesis that the two coefficients involving the STR term equal to 0 is rejected at the 5% level of significance. And once again, it has to do with high correlation between STR and PCTEL. So now we return to the application of this interaction analysis on the relationship between test scores and student-teacher ratio. So nonlinear specification will let us examine more nuanced questions about this relationship. So let's suppose if the first question that you are interested in is that are there nonlinear effects of class size reduction on test scores? What it simply means is that will a reduction from 35 to 30 have the same effect on test scores than when it's compared to a reduction from 20 to 15? And the second question that you are trying to explore is that whether the relationship between student-teacher ratio and test scores depends on the percentage of English learners in the classroom. So how do we approach both of these questions? Because the answer or the approach to answering both of these questions will be slightly different. So let's take a look at those. So for the first question, you will have to estimate linear and nonlinear functions of STR. If you are trying to see whether the effect of changes in STR at different levels of STR is different, then you have to introduce a quadratic term, a cubic term, for example, in order to see nonlinearities in the relationship between STR and test scores. And you should also see whether adding these nonlinear terms makes an economically important contribution or difference. So what it simply means is that you should not only be concerned by the quantitative difference which arises because of this adding these nonlinear terms. You should also but more importantly than that, you should be looking at how much is the real world importance of introducing these nonlinearities in the relationship between student-teacher ratio and test scores. And finally, you should also test for whether these nonlinear terms are significant or not. So how do we answer the second question, in which you are trying to see whether the relationship between student-teacher ratio and test scores depends on different values of percentage of English learners in the classroom? So for that, you will need to introduce an interaction term between student-teacher ratio and percentage of English learners. If the specification that you are using is nonlinear, meaning you are introducing quadratic and cubic terms for STR, then you need to add interactions with all these terms so that entire functional form can be different depending on the level of percentage of English learners, meaning you will essentially be adding interaction terms for HIEL multiplied by STR, HIEL multiplied by STR square, and HIEL multiplied by STR cube. So going back to the previous lecture, the first part of this chapter, we basically found out that the linear log function, or the linear log curve, and the cubic curve resulting from the cubic regression are pretty much the same, but the cubic regression offers us less accuracy than the linear log regression. So if I am a researcher who is interested in the effect of, in the relationship between student-teacher ratio and test scores, and I am also wary of the fact that there might be non-linearities in this relationship, as well as the relationship might differ when taken into account the percentage of English learners in the classroom. So I will simply start off with the first specification, in which I just have student-teacher ratio and the percentage of English learners, as well as the percentage of eligible students for subsidized lunch as my baseline regression. So you can see that the coefficient of student-teacher ratio is significant at the 5% level of significance, so at the 1% level of significance actually over here, but it does not include any sort of non-linearities in this relationship, and also does not have any sort of interaction terms. So as the second regression equation, or the second specification, I can add all of the control variables that I have access to. For example, the control variable that I did not add in the first specification was average district income, and the log of that, and obviously that will have an impact on the test scores. So when I include that, you can see that some of the effect on in the relationship between student-teacher ratio and test scores is taken away, and that might be the case because omitted variable bias might be reduced when you are including this average district income, the log of this, as one of the control variables. So now, if we believe that the relationship between student-teacher ratio and test scores will be different at different levels of percentage of English learners in the classroom, then we can move on to our third specification, which also includes this interaction term between high EL, which is a binary variable, takes the value of 1 when the percentage of English learners in the classroom is greater than equal to 10%, with the student-teacher ratio. So when we include this interaction term, you can see that there's no significance on this interaction, on the coefficient of this interaction term, as well as on the coefficient of student-teacher ratio. So we can move on to our fourth specification, in which we are also including all the other control variables, meaning the subsidized lunch control variable and the average district income control variable. But then again, this also does not show a significant relationship between student-teacher ratio and test scores, although the control variables that we have introduced are significant at the 1% level of significance. So We can move on to our fifth specification, in which we are basically also allowing for non-linearities in the relationship between student-teacher ratio and test scores by introducing the square and a cube term, while also controlling for all the other control variables that we have access to. In this scenario, you can see that the significance on the coefficient of student-teacher ratio comes back, and also the squared student-teacher ratio coefficient is also significant at the 1% level of significance. It points to the possible existence of non-linearities in the relationship between student-teacher ratio and test scores. Finally, moving on to our sixth specification, we also add the interaction terms because we believe that the relationship between student-teacher ratio and test scores might be different at different levels of high EL, which is the percentage of, which is the binary variable for the percentage of English learners in the classroom. And that is actually turns out to be true because these interaction effects are significant at the 5% level of significance. All three of these are essentially significant at the 5% level of significance. So this essentially is our most complete specification, where we allow for non-linearities as well as allow for interaction between the student-teacher ratio and high EL. So our seventh specification is for when we don't have a binary variable for English learners, but we have a continuous variable for English learners. And overall, you can see that the coefficient of student-teacher ratio in all three of these situations is changing, but also the total effect will depend on these other nonlinear terms that we have introduced, as well as the interaction terms in some of these specifications that we have introduced. So this table also shows, is related to the table shown on the previous slide, and it basically shows us the results for the hypothesis testing for joint hypotheses of different kinds. So for example, this first row includes the joint hypothesis that all the variables, including the variable str, meaning when str square is included, when str cube is included, when the interaction terms between str and high English learners is included, are all equal to 0. So in all of these specifications, we can see that this joint hypothesis is rejected at the 1% level of significance. The second row shows us the joint hypothesis that the nonlinear terms are equal to 0. And this joint hypothesis is also rejected at the 1% level of significance in all three of these specifications where nonlinear terms have been included. And lastly, this third row includes all the interaction terms, and we are testing for the joint hypothesis that all of these are equal to 0. And this joint hypothesis is also rejected at the 5% level of significance. So what can we conclude about question 1 then? So we can conclude that since we fail to reject the null, we reject the null hypothesis that both of the nonlinear terms are equal to 0, it means that there is presence of nonlinearities in the relationship between student-teacher ratio and test scores. And what do we do? What do we answer about question 2? Once again, we can see that the interaction, the joint hypothesis that the interaction, the coefficients of the interaction terms are equal to 0 can be rejected at the 5% level of significance, which once again shows that there is presence of interaction between student-teacher ratio and high EL. So an easier way to see what the line of best fit or the curve of best fit in the case of nonlinear specification comes out to be is to actually see them on the graph. And over here we have specification number 5, number 7, and number 2 plotted. You can see that the number 2 specification is a linear specification, and the cubic ones are number 5 and number 7. So overall they're all pretty close to each other, but the only difference that I would say is that at higher student-teacher ratio, the relationship in both of the cubic regressions becomes flat when it comes to the effect on test scores. Now this over here, these two lines or curves come from the specification number 6. Let's just take a look at that specification once again. So in this specification, we have introduced the nonlinear terms for STR while also including their interaction effects. So in this, both of these curves basically show that for most of the data, or where most of the data lies, meaning in this region over here, you can see that the slope when HIL is equal to 0 and when HIL is equal to 1 is pretty much similar to each other. But as far as policymaking is concerned, it still show a difference of at least 15 to 20, for at least 10 points between the two lines. So what it means is that for HIL equals to 1, on average for every student-teacher ratio, the test scores are lower than when HIL is equal to 0. So in simpler terms, what it means is that when there is a lower percentage of English learners in the classroom, on average, for every student-teacher ratio, the test scores will be higher for when there is a greater percentage of English learners in the classroom. So as always, the graphical representation tells us a lot about the relationship between whatever relationship we are trying to study. And in this case, we can see that the effect of student-teacher ratio on test scores does not change by much, because in this portion of the line or the curve where most of the data is lying, the slope pretty much remains the same for both of these lines. But as a policymaker, you can see that there is a difference between the average test scores when there is a higher percentage of English learners in the classroom compared to when there is a lower percentage of English learners in the classroom. So to summarize all of this, all the nonlinear regression functions, we can use functions of independent variables such as logarithmic functions and also quadratic and cubic functions, as well as interaction terms to allow nonlinearities in our relationship between the variable of interest and the y variable. The estimation and post-estimation techniques as far as hypothesis testing are concerned remain the same as in the case of multivariate regression or in the case of univariate regression. The interpretation of the coefficients will be model specific, meaning whether you're using a logarithmic model or a quadratic model or an interaction term model. So always be careful about interpreting the coefficients because that will change. The way you interpret will change depending on which model you will use. And as always, you should use your judgment as far as what economic theory is guiding you, and you should always try to see the specification that it is guided by the economic theory. And the economic theory will basically tell you whether you should include an interaction term or a nonlinear term as far as a logarithmic or a quadratic term is concerned, or both. So always try to do what makes sense in your application. Don't be mechanical about this. And the economic theory driving the relationship should be guiding your model specification or the choice of your model specification. So this was it for nonlinear regressions. I hope you guys had a good time listening to this lecture, and it added to your knowledge of nonlinear regressions. Until next time, take care, and thank you for listening.